Welcome. My name is Michael Smyers. I'm the SVP of Architecture at Zipwhip. When I had originally decided to do this discussion, I was going to do it on carrier grade uptime, but it's just a redundant talk about redundancy. It's just redundant, so we're not going to get into it. Instead, I'd like to talk about some cool stuff that I do at Zipwhip, so that we use Cassandra on. I think that's way more of an interesting talk. I'm going to talk about three different things. The first is who we are as a company, what we do, to give you some context, because otherwise it's like you're solving what problem now? The second thing is the use case that we actually use it on, which is signal delivery, spoiler. And then the third thing is the future goals where I'd like to use Cassandra in the future. Let's get started. So who is Zipwhip? We're a startup in Seattle. We're located in Queen Anne. And we do a lot of things. The easiest thing to say is that we are bringing texting into the internet, into the cloud. The more explicit way to say it is that we are text enabling existing landline telephone numbers. Now, before all of you guys roll your eyes about landlines going the way of the dinosaur, I actually think that, and we're finding that landlines are here to stay. More specifically, business landlines. Not really consumers. Consumers all have mobile phones, but businesses have their phone numbers, and that phone number is something they've invested a lot of money and time into. Take, for example, the taxi company. They print that number on the side of their car, and then they bring that number with them forever. They've had this. We've even had customers that had the number since, like, I don't know, the 50s, whatever. Same phone number. So we originally were thinking, oh yeah, let's do a Kickstarter. Let's get LCD displays on the phone for that picture right there. But we found that next to every landline telephone is a screen, an existing screen. It's either a computer or it's a tablet, it's your other phone, your mobile phone. So what we do is we bring the text messages to all of your displays for your phone number. Now, right now, what I'm going to talk about is the landline stuff, but we also do that for mobile. Very similar to iMessage. I'm not saying they copied us or anything, but I'm not saying that either. So let's, yeah. So yeah, we text stuff. All right, next. Text messages, SMS and MMS.
Personal.
Well, personal and business, yeah. Yeah, if you have an Android phone, this is a pivot we've done. We've been in business for about 7 years. We're still a startup. One of our pivots was on my mobile phone, which is an Android phone. If you text my phone, an SMS or an MMS, it pops up on all my devices. And if I read the message on my desktop, it cascades that state down to my phone. So that's one of our side businesses. I shouldn't say side, previous businesses, previous to landline. So, current carrier customers. One of the benefits of working in the landline texting space is that you get to work with carriers. So, yeah, that's exciting. Luckily, that's not my department. So, yeah. So, we're way better. No, all right. So, Twilio is an API. They text enable new landline telephone numbers, and they give you an API. We text enable your existing landline that you've had forever. We don't give you a new number. And we provide the end clients and the API. Which I'll get into in the next slide, kind of jumping ahead, with how the texts route. There's also some differences in how they route. So last week, 2 weeks ago, we launched Frontier Integration. They're a landline carrier on the East Coast. We text enabled all of their millions of lines. What they do is it's branded Frontier, it's a website and an iPad app. And when someone calls in to get voice service, they say, hey, do you want to add $5, $10, depending on your package? Do you want to add texting to your service? We have a rev share with them. It's all branded, but it's all through our network. So the reason I mentioned that is they sell like tens of thousands of new landlines a month. The landline space for consumers is on a decline. The landline space for businesses is very healthy. And one thing I wanted to mention is the previous slide that I'm remembering now is that we also text enable 1-800 numbers. So we have the ability to text enable 1-800 Starbucks. And I could turn on the White House right now and it would take 5 minutes. But if you're watching, I've never done that. All right, so carrier grade cloud texting. So I don't really want to get into how it works too technically detailed. However, I just want to show you where we sit in the routing system. So back in the day, if you had an AT&T phone and you texted a Verizon person, it just kind of went into dead null. It didn't really go anywhere. And in the late 90s, some companies came up and they started what's called the intercarrier ecosystem. They connected to all the carriers individually, because back in the 90s there were a significant number of them. And then they kind of become the third party, because a lot of the carriers don't like doing business with a lot of the carriers. Number one, logistically, there's too many of them, and number two, politically, they just have a lot of politics. So when you text from AT&T to Verizon, it goes through the intercarrier system. Now, if you're on AT&T and you text a landline telephone number, it goes through the intercarrier system and it goes to us over the internet, over IP, not through the SS7 networks. And we then route it to all your devices through the internet. So there's three that are called, there's a word for it, I forget. There's three of them. One of them went out of business, so there's really two. It's Cineverse and SAP. Yes, we have connections with both of them. Yeah. I don't really want to get into too technical detail about the contracts, but we also are one of those as well with some of the carriers. We are the partner that all of their texts go through for landlines and toll-free. So when you asked about Twilio, they're one of our customers. We're a routing avenue for them. The point, though, is that a lot of messages go through our network, even messages that aren't destined for our customers. Okay, so one of the challenges that we have is that we cascade the events down to all your devices. I don't know how many of you have lots of computers or devices and you use Skype, because they totally do not solve this problem. If you receive a bunch of messages on Skype and you go to your other computer, you're like, oh, I've got a lot of messages. Yeah, just kidding. You don't have any messages. They're all 2 days old, 3 days old. We, being a good product, we actually cascade the reads and the deletes through all your devices. So when you mark it as read on your desktop, it cascades it down to your phone. Well, if you, so that was the mobile product. The landline product is all of your connected devices, your iPads, your tablets, etc. So, as the last slide on Zipwhip, I promise, this is just a close-up of our web product. We do more value-added services on top of texting. We do conversation tracking on read counts. We do spam detection. We do filtering. That's one of the reasons that the carriers chose us as an aggregator, is because we provide services that the other companies don't. We provide spam filtering services, etc. So yeah, that's close to our product. You can see that the bright blue is unread and the light blue is read. Yeah, and then the white one's an outbound text. It's also for VoIP phones because it's all about the phone number. It's beyond just the way that the texts go through the copper line. It's the routing number in a database through the intercarrier system. So Google Voice uses landline numbers. They're powered by, actually purchased a whole block of landline numbers, and then they go and they multiplex them, which we have a patent on that, but I'm not going to. We have a patent on multiplexing phone numbers for an infinite number of users over a finite set of phone numbers. So, what are the use cases for Cassandra? We have two big use cases. The first is the most obvious, and it's at the bottom. It's message storage. We have a lot of messages that go through our network, and we need to store them. That is actually coming soon because it's a huge deal. This is very difficult to do. Just because being a carrier-grade system, we cannot have a 2-hour outage window at night. That's just not in the cards. So that's going to be more of a long migration process. Say what? Oh, MySQL. We're currently using MySQL to store messages. I actually have a slide later on about that. But we federate 5 masters, and then each of those masters have slaves, and the message traffic goes to a home. And each person's assigned to a home. Okay. We use Cassandra for signal delivery, which is event sync. Well, the benefits of the signal server in general are event sync, which is who's connected where, sending the message, making sure they don't receive the same message twice, making sure that they receive it in order. And then also privacy is who's getting a copy of my text. One of the interesting problems that we experience or we have to solve in the landline space or the multiple connected devices space is that you're not always in possession of all your devices at all times, and you want to know who's receiving my text. Your phone doesn't have that problem because it's your phone. Presence is assumed. You have it in your pocket. But you don't walk around with your 4 iPads in your back pocket. So we have to know who's receiving your text. That's one of the interesting problems. So presence and signal delivery. Signal server, which is the product that we use Cassandra for. So the signal server has a number of benefits. When this signal server was designed, version 1, we're actually on our 3rd or 4th iteration, we always had to have a connection always on to your device because Google Push and Apple Push didn't exist. Like I said, we've been in business for 7 years. So nowadays, we don't have it necessarily always on. It's on when your app is open. We use Google Push and Apple Push when your device is closed. I mean, when your app is off. We do maintain presence. Because Cassandra provides for us active data center capability. This signal server scales horizontally, which was the primary, scaling horizontally and redundancy was a primary design goal of the system. We have nameless nodes, which means similar to how you scale Cassandra, you just fire them up and it just gossips to each other. Our signal server does the same. And it's 0 configuration, which is really, really important for me, because with midnight, when I'm getting woken up because something's going wrong, I'm not at my peak brain intelligence, so I need to be able to just go hit the big red button, it fires up 10 more of them, and it just starts taking more traffic. Oh, an interesting thing as well is that we don't have a back-end portion and a front-end portion to the signal server. It's just a single jar that does both sides, and then we just copy it. And we can use load balancers to determine which ones we want to have, or how many we want to be back-end or front-end. So how do we scale a system, which is like I said, the primary design goal. So we can just flip on more Cassandra nodes. And the way that works, I'm sure all of you know, is that it just gossips to itself, figures out who is the most heavily used node. It takes on half of their work, and then transfers it over, and then gossips to each other with a new topology. And then our system is similar, is that we just fire up more. Our signal server binds into a central active MQ broker, or set of brokers. Binds into a central Zookeeper, and then Cassandra. I'm not really a big fan of Zookeeper, actually, now that I've had a chance to use it in a carrier-grade system. We have 3 or 4 of them, and wouldn't you know, they seem to crash at the same time, which is great, which is really great. We actually don't store anything on Zookeeper more than a couple milliseconds. We just use it for locking, cluster locking, and we only lock by the user ID, so there's not a lot of lock contention. It's not like you receive 1,000 texts on the same account, but just at the same second. That doesn't happen very often. So Zookeeper has one job, okay? One job, and it doesn't do it very well. So, specific Cassandra use cases. We have 2 things that we use Cassandra for, and I'm going to keep it really high level. I'll show you some code. When I say topology, we have 3 different types of topologies, but I'm only going to focus in on one. A topology is what we call this like map of who cares about what, or who's connected where. Like this binding of a lookup table is this high-level term that we call a topology. And then we have a timeline, which is the way that we store ordered events. Kind of a difficult problem to solve. This is something recent. Usually what we do is we just forward it in memory the whole way, and if you're not connected, you're SOL. But because we're providing what's called a backfill process, if you disconnect and reconnect, we want to provide for you everything you missed up to a period of time. We had to start storing them on disk, and that turns out to be kind of a hard problem to solve. I'm sure that there's lots of people that are smarter than me have solved this already, and if you did, we're hiring. Okay, subscription topology, who cares about what? So this is the great part of the discussion where I get to show you my code. I'm very proud of that. We have this very high-level thing called an address. An address describes your TCP/IP address, or your channel, events occur on channels, your channel address, or your client address, which represents your login, I guess, your client ID, your login to the account, to the system. I think that's about it, 3 of them. And so a topology binds addresses to addresses. That's the key thing that we use a topology for. The subscription ID is interesting. Our system allows you to bind multiple accounts on the same TCP connection, multiplex, and so we keep them straight with your subscription ID. Technically speaking, you could theoretically bind the same account 5 times on the same TCP/IP account or connection and receive 5 copies of the same signal, as long as your subscription ID is distinct. And so, forgot to mention, I'm glad I had it at the bottom. It's immutable data. You can add to it, but you can't remove from it. The best you can do is just forget your client ID, which is your token that represents who you are. You can't ever remove this stuff. So it only is written to when it first connects. That's why eventual consistency is okay for us, is that we don't have a lot of deletions in this data space. I was told that code is not the best way to communicate this, so I've got a diagram. So a good way to represent this is that a client address cares about multiple channels, and a channel cares about has many clients in it. So it's a good way to visualize it. The bottom left is how we put this in Cassandra. I have 4 column families that we store this data in. We have an active set, which is 2 column families, and we have a dormant set. So you can see that it has 2 ways of entry point. You can enter the data given a client ID, or you can enter the data given a channel. So we have our normal plus index, normal slash or index, 2 column families, and then we have our active and dormant. A row key is just address string 1, and then the column name is address string 2, vice versa. Pretty simple stuff. The reason we store the column value as the subscription ID is just in case some jerk wants to put an underscore in his subscription ID, I can do a string replace. Just in case. That actually happened. It was a bug fix. Okay. Subscription topology. So what we do is we create we use Stanionics for our Cassandra stuff. We don't use CQL. That was just because it looked really cool. And what was the company name? It was, who made Stanionics? Netflix, thank you. I was like, Netflix did it, so we should do it too. That was actually a discussion in our office. So yeah, what we do is we prepare a batch mutation. We serialize the address to a string. We iterate through all the channels that you want to add, and then we add them to Cassandra. Now, when you connect to our system, we copy everything from the dormant into the active. And when you disconnect, we delete it from the active. The reason is actually through testing, load testing, and performance testing. We found that the use case is that you get excited about getting a text on your landline, you log into your iPad, and then you put it down and never use it again. Or you uninstall the app, and we don't get a call back from that. So what we have is a huge buildup of all of these subscriptions, and so the app is spending 80, 90% of its time in actual real-world practice, ignoring forwarding of events. So it's like, oh, here's an event. We need to send this off to all the connected people, or no, I'm sorry, not connected. All the people who care, all the devices who care about this. Oh, this guy's offline. This guy's offline. This guy's offline. So what we did is we created this active topology, and our CPU usage just dropped to the floor. Timeline, events to deliver. Oh, back to subscription topology. Real quick about subscription topology is that the last thing I want to say on this is that this keeps track of who cares about which events. So therefore, it's a very, very, very read-heavy operation, read-heavy center of our app. Because our core infrastructure is called Zipwhip services. Zipwhip services will forward events blindly through JMS over to the signal server cluster whenever an event occurs. So if you delete a message or you read a message, it'll send those over. One of the use cases that we found through just practice, through use, was that most people receive texts when they're not necessarily reading the app or using the app. They're not necessarily actively there. So it creates a lot of traffic that is subsequently ignored. So the subscription topology helps us forward the traffic onto active nodes or ignore the traffic. Or I shouldn't say ignore, I should say not forward the traffic. So the subscription topology is very, very read-heavy. Conversely, the timeline is very write-heavy set of column families. Every event that occurs in our system, which is a message read, conversation change because of unread count, message delete, et cetera, it all hits the timeline. So the timeline's job is to write to disk in an ordered fashion and pull from disk in an ordered fashion in a system that is a clustered, nameless, very horizontally scaled system where nobody agrees on what time it is. So the timeline has 2 timestamps that we track. There's the occurrence time, which is when the event occurred. For example, they received a text. That's a very easy timestamp to gather because they received a text, it came to our SMSC, we have the time. Then the other time is the insertion time, which is, if I did my job right, 50 milliseconds after that. If I didn't, a couple seconds after that. So the 2 times we track individually, we write them with insertion time, and then we sort them based on occurrence time after the fact. This is a way to visualize it. We put the messages always at the end. Now, after I did this, this system, I had a talk with one of the DataStax guys, and he's like, "Oh, have you heard about time UUID?" No, I had not. I'm glad I've learned about that after I wrote this. So anyway, well, that's what we use Zookeeper for. But version 2, we'll use the new cool stuff that this guy was talking about. So we write to the end of the channel, and the T there is because this system doesn't just store messages. It doesn't just store conversations. It stores anything that's time ordered, and we put it at the end. The way we know that a user has received an event is through a watermark. Pretty standard system, pretty standard approach. Whenever someone receives an event, we just increment the timestamp. The previous version, this is just kind of a side note, not really Cassandra related, but just an interesting tidbit about building a system like this, is that we used to have version numbers, not timestamp based. So every time it was easy, you just add 1, grab the head, add 1, and then bada bing, bada boom. It became really challenging because you'd have holes in the data. Oh, it jumped from 13 to 15. Whatever happened to 14? What am I doing? With timestamps, it's really much easier to take events. For example, hey, you received this event, and then a second later, it got deleted. Why would I send down to the user, hey, you received an event, just kidding, you're going to delete it? If I, at the server, condense that, I've got holes in my data, and the client's freaking out. Oh, I didn't get my message. When in reality, I wanted him not to get it, because I want him or her. I wanted the device not to get it because it's just a waste of bandwidth, it's a waste of processing power. I just want to skip over the event entirely. Everything based on timestamps makes it really easy to skip over inconsequential data. Just one of the benefits of using timestamps. And they always seem to get bigger. Okay, so this is the code. What we do is we take in a message. Now it says message, but really what that should say is signal. We wanted the system to be open source eventually. Apparently Comcast beat me to it. They have this really nice system that they open sourced that does signal delivery. But what we do is we take in a message. Every message has an address of where it's destined to. It could be a server, it could be a client ID, it could be a channel. We grab a lock. We grab an insertion time, which basically is just current time locally, thanks to NTP. And then we release the lock, and then that's called the insertion time. The cool thing about that is that I don't have to write to Cassandra while I have the lock. I just have to get a timestamp that I know is unique. I need a timestamp. For each address, I need a unique timestamp. So it's okay if some other address has the same timestamp, but for a given address, it has to be a very distinct timestamp. That's how I know that your watermark is always moving forward. Imagine how crazy it would be if your watermark matched 2 messages, for example. So what we do is we append it. Now the transmit's pretty cool. That's why I put it up there, is I'm actually pretty proud of this. Because of each of these servers is both a customer-facing server and a backend server, it's possible that they've done the job of writing to Cassandra, and the guy that wants to receive the message is connected locally to them. Well, in that case, the connection returned by the connection manager would be a local client connection, a single one. Well, what happens if, because it's a decentralized system, a particular client ID, which is random, it's a GUID, and it's unique per device, happens to be connected twice, not only to me, but to that other guy over there? Well, we used to have a lot of locking through Zookeeper to make that impossible, but I've discovered that if I just allow one client to be connected to 2 places in a transient way, it all cleans up itself after anyway. I don't have to be so exact. So the connection returned would be a multiple connection of both a local client and a remote client through JMS. And in the topology, one of the topologies, which is called a client topology, a client address has 1 or more server addresses, and a server address has 1 or more client addresses. So it's just a way where we keep track of who's connected where. And the connection manager kind of wraps that complexity. So our code's pretty simple to read. It just says connection.send, and it may be sending to 50 people, it may be doing a no-op. It just depends. Now, this Cassandra layout's really easy. We just have a message timeline, and then the row key is the address, and then the column is the timestamp. That's why timestamps have to be distinct and unique, is that if you have, as you guys know with Cassandra, two column names with the same value would overwrite themselves. So, why did we choose Cassandra for this? Because it used to be Membase. I don't know if, and I was a big fan of Membase, because that's an enhanced version of Memcache, and I love Memcache. Memcache has done great things for us. Has anybody ever had problems with Membase? Well, let me tell you some problems with Membase. Number one, they strapped on SQLite behind their Memcache layer, which is awesome. That's really cool. Except when you have a significant level of I/O around the level of I/O we have, it keeps a transaction log. And when you restart Membase, it likes to verify and replay its transaction log to just load it back into Memcache. That's a very, very, very not fast operation, on the order of, 6 hours. So that was version 3 of the Signal server. We used everything in Membase, and we had our keys in Membase were just ordered IDs. When we switched to Cassandra, all of that went away, which was awesome. I don't know why Membase was crashing, but when coming back up, it was basically a light jump. Impossible. So every time any problem happened in Membase, we basically had to wipe our data, which was unacceptable. So with Cassandra, we have, I think the most important thing, the most important thing is the easy to scale, but the second most important thing is TTL. Our data with our use case is a very transient set of data. You care about the text you're about to receive. You care about the text you've received 10 minutes ago, but you don't care about the text you received 2 years ago. I mean, do you ever scroll up on your phone? No, nobody cares about that stuff. So if you're not connected to our system for a longer than an arbitrary period of time, let's just say 30 days, then all that data goes away, and you have to re-get a new client ID, and you have to require your data direct. You have to say, message/list to pull out the messages through web calls, old style web calls. What we do is we write atomically within the same data center, so it's a slower operation. That's really, really important, because our clients are programmed to know that there's 2 data centers, and it tries to connect to randomly either one. But once it picks one, it never changes data centers unless there's a big problem. And when it does change data centers, it slows down. It actually holds off for about 30 seconds to just allow the replication to happen across data center. So we have 2 DNS names. It picks one, and that's considered its home for the time being. And if it has a problem longer than 5 minutes, it switches data centers after a 30-second wait. The idea being that it will eventually become consistent, that the data that you want will eventually be there. That's one of the benefits that Cassandra brings. Let me say that a different way. That's one of the reasons how we are able to, Cassandra is one of the ways that we're able to be active data center. I tried really hard to make active data center work through MySQL, and it just wasn't the same. It was very difficult. And I found that I was spending all my mental CPU cycles on that instead of the layers above. So Cassandra really, really helped with our active data center. Yeah.
So were you doing like a consistency, like a local consistency level all, or how were you configuring the immediately consistent within the same data center?
The guy who wrote it's back there. No, I think what we're doing is we're doing all nodes in the local. So we reach quorum within the data center because all the reads are. No. We thought we had argued about this. The read is a single read, so all the reads are very fast. So we read from a single node. In order to make that happen, we have to write to all in the data center. Yes. It was because, it's configured differently for subscription topology versus, say, client topology, because one is very read heavy, one's very write heavy. The timeline is very write heavy. So the timeline was different. What was the timeline? Let's see. The timeline was read any. No, it was read quorum. The timeline was read quorum. The timeline is different. 80% of our events, 100% of our events get written to disk, but only 20% of them get read. So therefore, our write was a single, and our read was quorum. Yeah. That was right. No, our read was quorum. Yeah. I should have written this stuff down. Yeah. Okay. Milestones and product roadmap. Okay, so we love Cassandra for Signal Server. Yeah. I couldn't understand what? Oh, Cassandra, when you do a write, you can specify a TTL, and then when it does compaction, it removes all the tombstones. Well, I mean, yeah, but I mean the data is a 30-day TTL, so it's pretty old stuff. Yeah, it just runs on whatever Cassandra decides to run. Yeah, but we have so many nodes that it's not a big, we don't have like garbage collection outages or anything. Okay, so milestones and product roadmap. So we used Cassandra for the signal server really for two reasons. The first was the active data center reason, which was very important for us. And the second was to test it out and prove it out for a big heavy hitter project, which is the SMS storage. I really want to store our messages in Cassandra very badly. However, because I can't take an outage to do it, and because we have so many ways to access the message storage, it's a very labor-intensive process. Being a startup, we don't have a huge amount of labor to go and do the optional projects. I shouldn't say optional. I mean, it's important, but launching Frontier is a little bit more important than having Cassandra for message storage. So you have to be choosy, and we chose to do it with Signal Server first. Plus, with our operations team, getting the operational knowledge of how to configure Cassandra, how to tune it, just tuning the compaction levels, like that's all stuff we're learning through experience. Because in our startup, I'm sure it's, we have 30 people now, so are we really a startup? I think we're still a startup. But it's important for us to learn it through touching it, because it's hard to really learn the nuances through reading docs. So, plus, the way that we're scaling out the Cassandra Signal Server project is one device at a time. So we did the iPad project first, and when the iPad starts up, it makes a web call and it says, hey, I'm opting into the Signal Server with Cassandra. And so then, at that point forward, we send their traffic over to the new Signal Server system. And so we're scaling it organically with our expertise. So that allowed us to strategically choose not to become experts at everything. We chose to learn with demand because we have a limited amount of time. So we launched with 100 users, then we scaled it up to 1,000 users, then we scaled it up to 50,000 users. And as we continued to scale, we kind of learned as we went. And that was an important cost savings, honestly. It was just strategy of labor. So, okay. Thank you very much for your time. Any questions?